This is video 2 for the induction unit. To start this one, let's take a look at power production. 50 years after Faraday and Henry made their discoveries about electromagnetic induction, and a very famous engineer named Nikola Tesla and another engineer, George Westinghouse, put their findings to practical use and showed the world that electricity could be generated reliably and in sufficient quantities to light entire cities. Before this, it was kind of a novelty. You know, you could produce a little bit of electricity, but batteries could make more, so what was the point? So one thing that Nikola Tesla helped design was the turbo generator. These are really, really massive, massive generators. I have a schematic of one. And basically, it kind of uses part of the electricity being generated to make an even stronger magnetic field, so that as the wires turn inside that magnetic field, they're turning in stronger and stronger. So as it spins faster, the magnetic field that the wires cut through becomes greater, so you can make even more electricity. So it kind of uses part of its electricity to make more electricity. So that's why we call it a turbo generator. So Tesla then built these generators, and some of them, many of his designs are still used to this day. And they're a little bit more complicated than the simple models we've seen. But Tesla's generators had armatures consisting of bundles of copper wire that were made to spin within strong magnetic fields with a turbine. And then this was usually spun by either water falling over the turbine, like in a hydroelectric dam, or steam, which we've taken a look at several ways of making steam to make electricity. So we can take a look at this whole process from an atomic point of view. As the wire spins in the magnetic field influences the electrons to move in a certain direction. And then as the magnetic field changes its orientation, the electrons will move in the opposite direction. All right. The next topic I want to discuss are transformers. So it's interesting to see that electric energy can be carried across empty space from one device to another with a simple arrangement. And this is really, really cool. If I take two coils of wire and set them next to each other, and if I have electricity pass through one coil, I'll call that the primary coil. A magnetic field will be generated inside that coil. That magnetic field extends out into space, and if there's a nearby coil, which I'll call the secondary, it will influence the electrons in that coil of wire, causing an electromagnetic or causing the electrons to move, inducing a voltage. So we can carry electricity across empty space. And that's something that's really, really, really interesting and very important. So we could do this with a battery and a switch. Now, if you remember Faraday's law, in order to induce a voltage, we have to have a changing magnetic field. So usually this is going to be alternating current, because an alternating current creates a changing magnetic field inside the primary coil. And that changing magnetic field then induces a changing magnetic field inside the secondary coil, creating electricity, or the electrons to wiggle back and forth in the secondary coil. And again, we could do this with a simple battery and a switch. So if I had something like this, and then had a secondary coil, go to some sort of galvanometer or voltmeter or something. When you would close the switch, the electrons would start to move, and it would generate a reading just for an instant. Once these electrons become stable, once they stop accelerating and move at a constant velocity, you will no longer get a reading on the secondary coil. So another thing you could do, the moment you open the switch again, the electrons slow down to a stop. That gives a changing magnetic field, and then you would get a reading in the opposite direction. So for this first one, we would see when you first close the switch, the needle would deflect this way, and then it would go back to 0. And then when you open the switch, the needle should deflect in the opposite direction. So what makes this important is that we need a changing magnetic field for this to work. So transformers do not work with batteries. It's not like you can hook a battery up to a transformer and make this work. It has to be alternating current only, because we need that changing magnetic field. Now, if we were to place an iron core inside the primary and the secondary coils, the magnetic field around that primary coil will become intensified. It'll become stronger. This happens because there will be an alignment of the magnetic domains inside the iron. The field is also concentrated in the core and extends into the secondary, which intercepts more of the field change, and then the voltmeter will show a greater amount. So in other words, by inserting or using iron cores, we can make this whole effect stronger. So oftentimes we'll see a transformer kind of in this shape, where we have this iron core that's in the shape of a donut or a square, and then we just wrap wires around one side and the other. And this gives us our primary and secondary coil. The rate at which the magnetic field changes in the primary is equal to the frequency of the alternating current. So if I have 60 hertz of alternating current on the primary side, I will get 60 hertz of alternating current on the secondary side. And that's very important. We want to make sure that we have the same frequency of electricity. So, if the primary and secondary have equal number of loops, and we usually call these number of loops turns, then the input and the output will be equal. So, for example, if I had 1 volt of alternating current, and I attach it to a wire going around, on the secondary side, when I hook this up to some sort of meter, I will measure 1 volt of alternating current. I could have more than one wire on my output side. So here's my 1 volt of alternating current. And then let's say I had 2 galvanometers. Both of those devices would read 1 volt alternating current, which is really helpful. If the secondary coil has more turns than the primary, the alternating voltage produced in the secondary will be greater than that of the primary. So in this case, the voltage is said to be stepped up. So if the secondary has twice as many turns as the primary, the voltage in the secondary will be double the voltage in the primary. So if I had 1 volt of alternating current at my source, now I have 2 turns, this would measure 2 volts alternating. So I get more voltage coming out than I had going in. If the secondary has fewer turns than the primary, the alternating voltage produced in the secondary will be lower. So if I had 2 turns on the primary, 1 turn on the secondary, I would go from maybe 2 volts down to 1 volt. We call that stepping down. And we do that so that we can safely operate maybe an electric toy, train, charge a cell phone. The wall outlets are 110 volts. Your cell phone charger needs 5. So that big bulky thing that you plug into the wall is a transformer stepping down that 110 volts down to a safer voltage to charge your cell phone. So the relationship then between primary and secondary, it is linear, so we get to use proportions. So we have the primary voltage. And then we got the number of turns. Equals the secondary voltage over the number of turns on the secondary side. So the math is very, very simple and straightforward. Now, it might seem again that we're violating conservation of energy. Voltage measures energy. So how is it that we can step something up? It seems like we're getting something for nothing with a transformer. But we don't. You see, when the voltage is stepped up, more current is drawn by the primary. So we got this current that we have to worry about as well. The transformer actually transfers energy from one coil to the other. And the rate at which energy is transferred is called power. The power used in the secondary is supplied by the primary. So the primary goes no more than the secondary uses. So conservation of energy really does still play out. So in other words, the power in the primary equals the power in the secondary. So conservation of energy is still being upheld. Now, electrical power is the product of current times voltage. So what we could say then is that the current on the primary side times the voltage on the primary side must equal the current on the secondary side times the voltage on the secondary side. So then when we take a look at a step-down transformer, so let's take a look at some of these numbers here. On the primary, I've got 1,000 volts, and it's at 2 amps, and it has a power of 2,000 watts. That's on the primary. On the secondary side, notice we still got 2,000 watts, so the wattage is the same. We're stepping it down, so we're going from 1,000 volts down to 2,000 volts, but notice the current increases. So when we drop the voltage, the current must increase as a result. For a step-up transformer, so here I've got 100 volts, it's at 10 amps, and this time it's at 1,000 watts. On the secondary side, it's increased to 400 volts, but notice that the current has decreased. So we're getting more voltage for less amps. Power stays the same though. So a step-down transformer allows us to have more current available, and a step-up transformer means we have less current available. And this is kind of important for your home. High voltage power lines transport voltage at like 100,000 volts. I mean, it's really high voltage, but it's really low current. So when that really high voltage encounters the transformer outside of your home, that transformer steps the voltage down to 110 volts. Well, it's closer to like 220, but it steps it down to something that's usable for your house, but it also increases the amount of amperage available. And you'll remember earlier that one fuse can handle up to 15 amps. So that's what we do. When we step it down, we increase more current that we have available. But the power always stays the same. So if you have 2,000 watts at the electric power plant, you got 2,000 watts at your house. All right, that's going to conclude our unit on induction.